Okay, good morning, everyone. Welcome back to this session. So we've already learned a bunch of things about machine learning. We've had Ashish talk about digit recognition, right? That's a classification task, right? So let's start with a data set called the CIFAR-10 dataset. Has anyone heard about this dataset earlier? Yes. What do you use this dataset for? For classification of different kinds of objects. Right, so this says that CIFAR-10 dataset consists of 60,000 images, 10 classes, and 6,000 images per classes. And these are the types of classes. You have airplanes, automobiles, bird, cat, deer, dog, frog, horse, ship, truck. Right. Now let's look at an example and see what you think you'll be predicting. What is, let me actually hide the answer. What do you see as a human? What do you see in these images? Apples. What kind of an apple? Green apple. What do you think you'll predict using if you'd learned a model on CIFAR-10? Sorry? Why? That's a strange answer, right? Why do you think you'll predict a frog? So the data set, you're correct. The only green thing in the data set are frogs. So in this case, we end up predicting if you learn simple models, you'll end up predicting frog with high probability values. Does that make sense? No? Is this correct? Should we be doing something about this? What do you think would have been an ideal response? Sorry? Unknown item, right? That could be one. How else could you give a better answer? So you're telling the solution. So I'm asking, like, what do you think broadly we should be telling as an answer? You're telling how we can improve the answer. Okay. So what you're saying is a subset of machine learning. So yesterday Ashish touched upon semi-supervised learning. What you're saying is an example of that, and it's called active learning. So for instances you're unsure about, you should ask the human to label. Right? So that's one way to solve this problem. But before that, what do you say? What should the system ideally say? Rather than saying that it's with 99% probability that it's a green apple, what do you think the system should output? So what happens when you go in Vivas and the question is completely out of your league? What do you answer? We generally answer something we know, right? But what do you think should have been a good answer? I don't know, right? So the machine learning system should tell, I don't know. I don't know whether this is an apple or a frog or what this specific thing is. But generally, existing algorithms don't have this capacity, right? They don't have a notion of uncertainty in the prediction. Right? They're just telling with a high amount of confidence that this is a particular class, and this specific case, it's wrong. It's not the correct class. Right? Let's look at MNIST again. Also, before I forget, so all of these figures, slides I'm using, they have been years of work from, and I've taken a lot of help from my teaching assistants, from my students, from interns. So all of these images, all of these plots, all the slides have been a lot of work from them. So let's look at this particular image. Now, this is an MNIST dataset image, right? 8. We're saying that the probability that this is predicting 8 seems to be very high. Does this make sense? Seems to be correct. What about this image? It's a Lee t-shirt. What do you think should be the output? Similar to the previous question. I don't know. How do you quantify I don't know? Low probability, or we can place a high amount of variance when we're predicting this to be class 8, right? So we are unsure. So here the probability mass is very high. Oh, sorry, the density is very high. Whereas in this case, we see that the density is very spread. The maximum value, in fact, is also 10, right? Compared to the previous one. Again, I don't want you to be talking about the quantitative comparison between these numbers. All we're trying to say, all we want to be able to say is that for this specific example, maybe the confidence is not super high, right? That's what we want to be able to say. Let's take a different example. Now we are dealing with a regression problem. On within the two shaded lines, you're seeing the training data set, right? Beyond that, you're trying to predict. So what do you think about this prediction? Is it a good prediction? Is it a bad prediction? Why do you say it's a bad prediction? It's not able to fit well, right? The red is the prediction. It's not able to fit well, clearly. Now let's look at another figure. What do you think about this figure? Do you think it's a better fit? Why do you say this is a better fit? Sorry? It's getting more correct answers, but beyond that, it's also giving you a notion of uncertainty, right? So the shaded zones are telling you how, so in the dark shaded zone, you're saying you're very certain. As you've moved further and further away, you're not, the points are very unlikely to occur there, right? So you have a notion of uncertainty in your prediction, right? So that's the central theme that we're going to be touching. I just need to turn off my video first. Stop sharing for a second. The question I'm going to pose to you is that, how do we get this notion of uncertainty? How do you think we can get this notion of uncertainty in a machine learning classifiers or regressors? Yes, any thoughts on that? Sorry? No. So the question is, doesn't low probability automatically mean low confidence? There's a more sophisticated concept involved, which is known as calibration. But I don't want to get into that. For now, I'm going to just tell you that we need a more fundamental tool in order to be able to answer things like getting the uncertainty in our predictions. And that underlying principle is known as the Bayes theorem, right? So I believe all of us know about that. Actually, I should not have told you about that and ask you the question, but let's play a small game and let's see what you think.
The goal is for you to come away from this video understanding one of the most important formulas in all discovery. When used Bayesian certainty, so understanding. For rediscovery, you and I are going
to... Okay, let's...
Yeah. Makes it obvious. I'd like to tell you about a man named Steve. Listen carefully.
This is the question. We are talking about a person named Steve, and I want you to think about the answer.
Steve is very shy and withdrawn, invariably helpful, but with very little interest in people or the world of reality. A meek and tidy soul, he has a need for order and structure and a passion for detail. Which of the following do you find more likely? Steve is a librarian, or Steve is a farmer?
Okay, so, what do you folks think? How many folks think that Steve is a librarian? Shy, withdrawn, invariably helpful, little interest in people or the world of reality. Okay, how many people think Steve is a farmer?
Yes, I think he's a farmer.
Okay, so someone from the live audience thinks Steve is a farmer. What about the others? You don't think, or you don't want to give an answer? Yes. So why do you think Steve is a librarian? Anyone who's answered that? Yes, okay, good. Okay. 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 Okay, so that sounds like a very good argument to support your claim. Any other answers? Why? Yes. Yes. Library is a very organized place. You have books organized by shelves. Right? Makes sense. Thus far, what you said makes sense. But let's go ahead and see if. So, does anyone disagree with this answer? So those who said farmers.
Yeah, there seems to be more farmers in the sample space than a librarian. So simple.
Okay. Okay, so we'll come back to that comment in a second. So someone said, so someone from the online audience says that maybe the sample space has more farmers. Why do you think that is important? Yes, yes, yes. Yeah, so maybe that's also true. Yes. You can say the same thing, right? That's a valid argument. Let's go ahead with the video and see either way whether this line of thinking is correct or not.
You may recognize this as an example from a study conducted by the two psychologists Daniel Kahneman and Amos Tversky.
Okay,
Their work was...
Does anyone remember or know about these two people? Have you heard about this name? Thinking Fast and Slow? Anyone heard of the book? Okay.
Big deal. It won a Nobel Prize, and it's been popularized many times over in books like Kahneman's Thinking Fast and Slow or Michael Lewis's The Undoing Project. What they researched was human judgments, with a frequent focus on when these judgments irrationally contradict what the laws of probability suggest they should be. The example with Steve, our maybe librarian, maybe farmer, illustrates one specific type of irrationality. Or maybe I should say alleged irrationality. There are people who debate the conclusion here, but more on all of that later on. According to Kahneman and Tversky, after people are given this description of Steve as a meek and tidy soul, most say that he's more likely to be a librarian. After all, these traits line up better with the stereotypical view of a librarian than a farmer. And according to Kahneman and Tversky, this is irrational. The point is not whether people hold correct or biased views about the personalities of librarians and farmers. It's that almost nobody thinks to incorporate information about the ratio of farmers to librarians in their judgments. In their paper, Kahneman and Tversky said that in the US, that ratio is about 20-1. The numbers that I could find today put that actually much higher, but let's stick with the 20-1 number, since it's a little easier to illustrate and it proves the point just as well. To be clear, anyone who is asked this question is not expected to have perfect information about the actual statistics of farmers and librarians and their personality traits. But the question is whether people even think to consider that ratio, enough to at least make a rough estimate. Rationality is not about knowing.
So why do you think now knowing the ratio of farmers to librarian makes a difference?
You are making use of the information, right? When you are now coming with the answer. So earlier you didn't have this. So now you're trying to make use of it.
Okay. Okay. So couldn't helpfully, but I think largely on point. Yes, there's another. Yes, excellent. Excellent point. So if you're not told certain characteristics of this person, then if you just pick up any Steve at random, right? What is Steve more likely to be? A farmer or a librarian? A farmer, right? Why? Because there are just way more farmers than librarians in the US in this specific case. But now you have got some additional information about the characteristics of the person. How does that change your belief? So initially, let's say if I told you nothing, you'd say that it's most likely Steve. Oh, sorry, most likely a farmer. But now I've told you some information about the person's characteristic. Does that reduce the probability of this person being a librarian or a farmer? Why is that? Because you've added now some information or some evidence which points towards this person having some characteristics like a librarian. And this is a base rule which we've been exposed to for 5-6 years now. Let's just go through the video and we'll come back to
facts. It's about recognizing which facts are relevant. Now, if you do think to make that estimate, there's a pretty simple way to reason about the question, which, spoiler alert, involves all of the essential reasoning behind Bayes' theorem. You might start by picturing a representative sample of farmers and librarians, say 200 farmers and 10 librarians. Then, when you hear of this meek and tidy soul description, let's say that your gut instinct is that 40% of librarians would fit that description and that 10% of farmers would. If those are your estimates, it would mean that from your sample, you would expect about 4 librarians to fit the description and about 20 farmers to fit that description. So, the probability that a random person among those who fit this description is a librarian is 4 out of 24, or 16.7%. So even if you think that a librarian is 4 times as likely as a farmer to fit this description, that's not enough to overcome the fact that there are way more farmers. The upshot, and this is the key mantra underlying Bayes' theorem, is that new evidence does not completely determine your beliefs in a vacuum. It should update prior beliefs. If this line of reasoning makes sense to you, the way...
So stop this video at this point. So this was the key idea, that we'll have certain prior beliefs. We'll have certain beliefs when we have not had a chance to observe any data. In this case, the data was this specific characteristics of this person, right? We had certain beliefs, we got some new data, we have updated our beliefs, but maybe we didn't have enough data to overturn our prior beliefs, right? If the prior beliefs were, let's say, the ratio of farmers to the ratio of librarians is 1:1, then what do you think this person would be? Most likely a librarian, because the ratio of librarians to the ratio of farmers is approximately 1. So then all of the information is mostly carried just in the evidence presented to you, right? In the characteristics of this person given to you. So this line of thinking, where you start off with certain prior beliefs, you get some data, you update your beliefs. This is known as Bayesian view of thinking. Now, one reason we are discussing this Bayesian view of thinking is to get this notion of uncertainty, which we saw in the first couple of slides. I showed that we want to be able to tell that I don't know, or there is a huge amount of uncertainty in my regression or classification prediction, right? That's one way to look at it. And Bayesian view of learning also introduces a few terms which help us automatically derive the loss function. So what loss function are we using for logistic regression? Quick. Binary cross entropy, right? So Ashish yesterday presented why it makes sense, right? But where do you think it's derived from? Right? We look at that also in this particular presentation. That's why we are dealing with this formulation. So coming back to Bayes' rule, probability of A given B is B given A times probability of A times P of B. These are some terms we've seen many times. Let's work through a very quick example to ensure that we've got all the terms working. Let's say, unfortunately, someone tested positive for a disease in this time. So these slides were prepared pre-COVID. So now these things make a lot more sense. So you've tested positive for a certain disease, but the test is only 99% accurate. So why do you think I've written the word only 99% accurate? Does a 99 seem like a very good number? But 99 is a good number. So if you get 99% accuracy, you publish a paper, you'll get a. Let's say that the number of people they've tested is also large. But why do you think I've written this only 99% accurate? Sorry? Margin of error of 1% is?
Because the population is huge, right? So even
population is indeed huge, yes. Yeah. Is dangerous, okay. So he's saying that the false positive is dangerous. So false positive is you're falsely predicting someone who doesn't have the disease to have the disease. Why is it dangerous? Because they'll be placed in quarantine for no rhyme or reason. Right? Now you can probably relate to this fact. What about true false negative, right? Sorry? So in this case, actually 99% accurate means the probability that test turns out positive, that the disease is true, is 0.99. And the test turns out negative, that the disease is false, is also 0.99. So I'm just writing it this way. This is what I'm meaning by 99% accurate. There could have been different interpretations. But I still not got a very convincing answer as to why this 99% is not a good enough answer. Someone from the audience said something, but online audience said something. But so my argument was 99% accuracy in most papers will help you get the paper through and research paper. It seems like a very good number. Okay, one, we're not looking at the right metrics. Second, why do you think Ashish introduced dummy classifier? The baseline, right? The baseline numbers make a big difference. Secondly, the application context is required, right? So we'll see that why 99% accuracy is still not a very good number. Let's now work through the Bayes rule for this, right? We tested positive for a disease. Testing positive for a disease does not mean that you have a disease, right? But the important fact which we're missing is that the disease is a rare one, right? Disease is a rare one. In this case, it means that 1 in 10,000 people have this disease. So how do you think this changes? This changes your beliefs. Would you be more worried by knowing this fact, or would you be less worried? More worried? Why? One type of data. What type of data? It's a rare one, but let's assume that there is no sampling issues. Like when these probabilities were calculated, it was done on a fair enough sample. Yes. 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 Excellent. So again, I think we need to revisit our thinking. We get too carried away by just looking at this term that you've tested positive, right? But let's revisit the Bayes rule. We start with, you had certain prior belief. Let's say if all of us are sitting in this room, right? What is the prior belief that one of us could have had this disease? How do you think we'll calculate that? Maybe we look at the daily COVID cases in India, divide that by the total population. Maybe that's how low an event is. Or we look at it as a city level, at a block level, something like that. I'm just giving a very crude approximation. And that should just give us a lot of fame. That should just give us a lot of assurance that it's not a very widespread disease at this point in time. Let's just say that. So disease is currently a rare one. That's your prior belief. You have certain data that you've tested positive. Now you have to update your beliefs knowing this new data, right? How do you do that? Probability, I'm just using some shorthand notation. Test given data is 0.99. The test turns out positive given disease is positive is 0.9. Test turns out false, negative given disease is negative is 0.99. So therefore we can calculate the remaining numbers. Test turns out positive given that you don't have disease is 0.01. Test comes out negative given that you have disease is 0.01. The probability that someone has a disease is 10 to the power minus 4, and probability that someone doesn't have a disease is very high. 1 minus 10 to the power minus 4. This is the prior probability that you have. Given this, if you have to calculate that the probability of disease is true, given that the test has turned out to be positive, will be just an application of Bayes rule. The numerator is test is positive, given disease is positive, times probability of diseases, someone has the prior probability on a disease divided by probability of the test turns out to be positive. Right? This is just an application of Bayes rule. We calculate these things. The only thing which might be a little non-trivial is the calculation of the denominator. So how do you think we calculate the probability that the test has turned out to be positive? In what situations, 2 situations can the test turn out to be positive? The test turns out to be positive when someone has disease. The test can also turn out to be positive when someone doesn't have a disease. Sorry, we'll add up those cases, right? So someone can have test to be positive when the person actually has a disease, plus the person can also have the test turn out positive if the person doesn't have a disease, right? So this is the total probability that we are calculating for P of T. I'll just quickly skim over the results. I believe you would have studied this earlier. It's just you may be out of practice. So this number comes out to be 0.09, right? Which is significantly lesser than 0.99, which you would have thought, right? But the fact is that even 0.09 is a big number in such situations, even if, so specifically if the disease is a deadly one, right? So therefore it makes sense to, if this 0.9 number was instead 0.999, right? Something like that. Does that change your beliefs? Yes. Therefore, having a much higher amount of accuracy in these tests is required. Any questions till now? But why are we discussing this? Why are we discussing the Bayes rule in a machine learning class now? Why do you think? Has this got anything to do with what Ashish was discussing in the morning? He was not discussing about Bayes rule. He was not discussing about COVID.
I thought it's linked to the last calculation BC.
Okay. Yeah, you're on the right track. Someone from the online audience also made the answer that it makes the loss calculation easier. But let's see how this happens. So we'll now be using this same Bayes rule for machine learning, right? So we have previously used W to indicate what in the logistic regression case? What does W indicate? The weights or the parameters, right? I'm using the notation theta, right? I'm using the notation D to tell about observed data, right? So this is the application of Bayes rule for machine learning. The probability of theta, so what is your understanding of the parameters theta once you've observed the data, right? That is given by this Bayes rule, which has three terms: probability of the data given the parameters theta times the prior probability P of theta divided by probability of observing the data, right? Just think about this for a minute. Let me know if you have questions. We'll see each of these terms and we'll see how each of these terms relate to what we have studied in the previous 3 lectures. Yes, yes. Just a second. I'll come to that.
Sir, excuse me, sir.
Yes.
Am I audible, sir?
You're audible.
Sir, could you please explain the purpose of theta here?
Sorry, could I explain what is the question? Should I explain what?
Sir, purpose of theta.
Purpose of
Probability
theta.
Yes, sir. We can use any other variable.
So in logistic regression, W was the weights of the model, right? You were writing W, summation Wi xi plus B, and then you were putting a sigmoid function, sigmoid activation over that, and that was telling you your probability of output is y equal to 1. Right? That was the.
Okay, sir.
So similarly, I'm just replacing W with theta here. It's a bit of a in some machine learning textbooks references you'll see theta being used, and some you'll see W being used. Just
okay. Thank you, sir.
Yes. Any questions thus far on the Bayes rule? Okay, so now let's look at the individual terms. Theta given D, probability of theta given D is called the posterior, right? D given theta is called the likelihood. How likely are you to see the data given the parameters theta, right? P of theta is the prior and P of D is the evidence. So we'll mostly talk about the first 3 terms. In the interest of time, I will be ignoring mostly the P of D term because we don't require it for most of the calculations. Let's see what each of these terms mean. P of D given theta tells how good so it tells how you can quantify, you can generate the data given the parameters theta, right? The goodness of the fit. So it's in some sense a notion of the goodness of the fit. And the higher value tells you that the model is describing the data better, right? So some of these terms will keep getting more clear as we go ahead. Our prior is what we tell the model before we have seen any data. That's just what the literal meaning of the word prior, right? You've observed no data, or that's your prior belief about what the parameters would be, right? So let's think about this problem. You're trying to solve logistic regression, right? So you ask someone that what do you think is the distribution of the parameters W or theta, right? So this is what you encode in the prior. Maybe you say that my parameters are uniformly distributed from -1 to 1, right? That's one kind of a prior you could have given. Likelihood tells how good is so it just tells you that how likely are you to observe the data set that you're given a certain parameters theta. Posterior is once you've observed the data, how do your beliefs about your parameters change, right? Similar to the Bayesian update, which we had for the Steve librarian example, you started off with certain prior knowledge that the number of librarians to the number of farmers is certain ratio. The likelihood is denoting how likely is this person a librarian given the characteristics. Posterior is once you have observed the data and you have incorporated the prior knowledge, then how likely is this person, like you're trying to encode this person's behavior. Will this person be a librarian or a farmer? So we'll come on to now a very specific example called the coin toss problem, right? So let's assume that we had a coin, we flipped it 10 times. We got head, head, tail, 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 head, head, tail, tail, tail. So we got 4 heads, 6 tails, right? So what do you think is the probability of observing a head? Four out of 10. Why do you think that? Okay. Does everyone agree with this answer? That you observe 4 heads and 10 flips. So it makes it, you're saying that you're just using the statistically, you're just looking at the running frequency. Should it be half? Why should it be half? Okay. Okay, excellent. So we have 2 answers, both of them are correct. But then we'll have to come to finally a single answer. So one of the participants said that the probability of heads is 0.5 because we're assuming it to be an unbiased coin, right? The other participant said that I have tossed the coin 10 times, I've got 4 heads, so the probability of heads has to be 0.4. Which of them is the correct answer? So yes. Yes, yes, yes. Okay, so all of you have given good answers. Let's walk over the answers. So you'll probably think about 4 over 10 because that's the notion of probability when it's defined as a measure of long running frequencies. You run an experiment 10,000 times, 1 lakh times, and you observe the number of heads to be whatever number. You just divide that ratio, the number of heads to the total number of samples, and you say that that's the probability. Right? That's one interpretation of probability. The other is, what is the likelihood of seeing this above sequence or observing 4 heads when probability of head equal to theta, right? This is a slightly complicated statement. How likely will you see 4 heads, right? What is the likelihood of seeing 4 heads when the probability of heads is equal to theta? Theta is some number now. It's some fraction. Okay, that's the correct answer, but how do you get that? The order here does not matter. So we're not looking at, we are just looking at 4 heads. We're not looking at this specific order. Sorry, we are looking at this specific order. The order does matter here. So how many of us have heard about the Bernoulli likelihood or the Bernoulli distribution? How many? Can you just raise your hands? Okay, how many of you have heard but forgotten? Okay, so that's what I'm trying to do, so that all of the things that we study in mathematics, we are able to code them up and we are able to relate them to our other courses, so that these things are not disjoint. So let's look at this particular slide. Okay, let me just walk over this. The probability of heads is theta, right? Probability of tails has to be 1 minus theta. Right? Does everyone agree on this? So let me actually just show you the Wikipedia article on Bernoulli distribution. Right, so the Wikipedia article also says that x is a random variable. The distribution probability of x equal to 1 is given by p. I've written it to be theta. So look at p as theta, and the probability of 0 is 1 minus theta. Sorry, the probability that it's tails in this case is 1 minus theta. And I have a notebook also to show this. Is the text clear? You can see. You don't need to worry about the exact syntax. I just want to show some examples first. And we'll also run through the same notebook in the last session also, in today's tutorial also. So I'm creating a Bernoulli distribution object with probs equal to 0.3. So this means that the probability of one I'm encoding as heads and 0 I'm encoding as tails. Right? The probability of heads is 0.3. Right? So I've created this object, and next I'm just printing the probability of 1 and 0. It turns out to be 0.3 and 0.7 as expected, right? So again, remember probability of 1 means probability of getting a heads, and probability of 0 means probability of getting a tails. Now, if we look at the probability mass function, right? So it looks something like this. The probability of heads, which is indicated by 1, is 0.3 and the other one is 0.7. It's a very simple probability mass function. If we change something here, let's say we change this 0.3 to 0.4, you'll see that this graph changes ever so slightly, but nothing very sophisticated thus far. Let's put it back to 0.3. Right. So before we go into the details of modeling the above data, the coin toss data, let's see if we had to sample some data from a given distribution, right? So if we have to sample some data from a Bernoulli distribution, what do you think will the samples look like? You have a Bernoulli distribution, right? And your probability of heads is 0.3, probability of tails is 0.7. If you were to draw some samples, what do you think those samples will be? Will they be 0.3, 0.4, 0.5, 0.6, 0.7, or will they be head, tails, head, tails, head, tails, tails, something like that? Head and tail, right? So you're creating this Bernoulli distribution for heads and tails, for the coin toss problem, right? So if we create some samples from this distribution, they will be heads and tails, right? Each sample will be head and tail, right? So let's just try and get a single sample. Again, don't worry about the syntax. This sample, if I get a single sample, it turns out to be a 0, which means it's a tails, right? But let's see if we were to generate more samples, then do we see certain characteristics of the samples or not? Now I'm generating 10 samples. And how many heads do you see in this? 3 heads. Maybe if I were to change the C to, let's say, something else. How many heads do you see now? 1. Why do you think this is happening? So we're dealing with random experiments, and probability of 0.3 does not necessarily mean that you'll get 30% of the samples to be heads, at least not in the small data settings. If you had very large amount of data, then this property will hold. And let's try and do that. So now I'm generating 10,000 samples from the Bernoulli distribution. And I'm getting approximately 3,000. Approximately 30% of those samples are heads, 1, and therefore the 70%, about 70% of the samples will be 0 or tails, right? Any questions thus far on the Bernoulli distribution, how to instantiate it, how to get some samples from it? Okay, so yesterday we had heard of a term called IID. Can someone remind us what that meant? Okay, so now can you tell me what do you mean by IID by looking at the above code? Excellent. So that's the independent aspect. What about the identical? Yes. Excellent. So we want to generate some samples from a given distribution, right? Their samples or the data is IID, independent, identically distributed, right? So independent samples means that if I had a tails in the current sample, right? Then does that impact whether the next time I toss a coin, will it be heads or tails? Right? They're independent. So sampling is independent. What I got at time t0 does not impact what I get at time t1. right? And so on and so forth, the time t2. So that's the independent notion of IID, identically distributed. Each time I'm getting a sample, I'm using the exact same distribution, exact same Bernoulli distribution, or the Bernoulli distribution with the exact same parameters or the instantiation, right? That is meant by identically independent and identically distributed. To understand this further, so we have a distribution Bernoulli, a distribution object Bernoulli. I'm generating n samples IID from this, right? N independent identically distributed samples. So I get a sample. I'm using the exact same object each time. So if I use the exact same object, then which condition is being met of IID? Identical. I'm using the identical distribution to generate samples. Second, independent. This sample of I, the ith sample, has got nothing to do with the I minus 1th sample. Right? So therefore, this data is IID generated. Right? Any questions on this?
No, sir.
Okay. So we could have also just written this in a, without using the for loop. We could have generated these samples. So let's now look at the coin toss problem again, right? And let's see that, let's assume that this is the data set that we have got. So previously we had 4 heads and 6 tails, but let's assume that this is the data set that we have. So 1, 2, 3, 4, 5, 6, 7, 8, 8 heads, right? Now, is the probability of heads 0.8 given this data set? Again, that will depend on whether or not we incorporate any prior knowledge, right? Let's assume that we don't incorporate any prior knowledge. In that case, can we say that the probability of heads is 0.8? Right? But how do we say that? For that, now we're looking at the Bernoulli distribution, right? And the concept of, go back to this slide. The concept of the Bernoulli distribution would be used here. So we come back, we say the probability of heads is theta, probability of tails is 1 minus theta, right? So then what is the PMF for the first observation of D1? So D1 is either heads or tails, right? Of it being X, where X equal to 0 for tails and X equal to 1 for heads. How do you think we can write probability that the first sample is X, right? So the easy way to think about this is, if X equal to 1, then what is the probability of D1 equal to 1 given theta? If X equal to 1, it means if you've observed a heads, what is the probability of observing a head given this distribution? P of head equal to theta and P of t equal to 1 minus theta. Theta, right? And what is the probability of observing, if X equal to 0, what is the probability of observing D1 equal to 0 given the theta parameter? 1 minus theta.
1 minus
The
theta.
probability of getting a heads is, if X equal to 1, probability of D1 equal to X given theta is theta. If X equal to 0 means you get a tails, then the probability of tails is 1 minus theta, right? Now, all we were trying to do is to just write this in a more convenient fashion. So can we write like this? Probability of D1 equal to X, X is either 0 or 1, given the parameter theta is theta to the power X times 1 minus theta to the power 1 minus X, right? Right? So just think about this expression for a second and just substitute X equal to 0 here. If you put X equal to 0, then probability of D1 equal to 0, or the first data point is a tails, given the parameter theta is theta to the power 0, which is 1 times 1 minus theta raised to power 1, right? So probability of D1 equal to 0, D1 equal to tails given theta is 1 minus theta. If X equal to 1, probability of D1 equal to heads given theta is theta to the power 1 into 1 minus theta to the power 0, which is theta, right? So can we recover the fact that probability of heads is theta and probability of tails is 1 minus theta, right? So for the first sample, the probability of D1 equal to X is given as theta to the power X times 1 minus theta to the power 1 minus X. Yes. Any question in this? Okay. And we can just verify we just did this. Okay. What is the probability of D1, D2, D3? So let's say we had n observation, n equal to 10 observations, given the parameter theta. How do we write that?
Anyway, it is IID, right? So we can multiply the probabilities.
Sorry, I didn't get your answer.
No, I said, so if you are looking at a specific combination of 10 tosses, so we can multiply for each of the things, right? For example, first is a head, we can say probability is theta.
Yes.
Next is a tail, 1 minus theta. So basically theta to the power of number of times heads into 1 minus theta to the power number of times tails, right?
Yes, excellent. So the important thing here is, so we studied this term called IID, right? So why do you think the term IID was introduced, and how does it help you to write this expression in an easier fashion? The probability of D1, comma D2, comma Dn given theta is equal to what? How can we simplify this expression? Yes, excellent. So does observing a heads in the first sample and then the first sample, does that tell you anything about what you'll get in the next sample? No. So then can we factorize this probability into something like, okay, sorry. Something like this. There should have been a conditional here also. The probability of the data set, which is D1, D2, D till Dn given theta, is P of D1 given theta into P of D2 given theta, so on and so forth till P of Dn given theta. Does everyone agree on this statement? Any questions on this? Right. So why can we write it? Why can we reduce this expression in this particular way? Because of what property? IID assumption that we had made. So D1, probability of D1 and D2 given theta is this D1 given theta times D2 given theta, right? So this is a very important concept to remember. If we have this particular statement written, then probability of D1, Dn given theta is theta to the power number of heads times 1 minus theta to the power number of tails, right? Does everyone agree on this? Theta to the power number of heads times 1 minus theta to the power number of tails. Number of heads plus number of tails is n, right? Any questions on this? If there are questions, I can write slower and explain this also. Okay. So this particular term is probability of the data given theta, right? But if we go back a few slides, do we see the same term again? P of D given theta. Right? So this term, we said that is called the likelihood term, right? So our goal here in this entire work is to get an estimate of theta, right? To get what is the best estimate that for theta, which can tell us about this data, which can best explain this data, right? So we said that given a data set D, we'd have this probability of the data set given theta, which is also the likelihood term, is theta to the power number of heads times 1 minus theta to the power number of tails, right? So we define this, we call this the likelihood function. It's a function of, what do you think this likelihood is a function of? Is it a function of the data or is it a function of the theta parameter?
Theta.
So the data we assume to be fixed. Once you fix the data, then the likelihood is a function of theta, right? So think of this. How likely are you to see 4 heads and 6 tails if probability of heads is 0? What do you think? You'll never see 4 heads and 6 tails if the probability of heads is 0. How likely are you to see 4 heads and 6 tails if probability of heads is 0.4? How likely are you to see 4 heads, 6 tails if the probability of heads is 0.4? I don't want the answer. I'm just saying. Will it be a low number or a high number? So will it be lower than when the probability of heads is 0? It will be a higher number than that, right?
It will be a higher number.
It's more likely. So we can go back to the notebook. So we can create a graph like this, right? So this is the probability of D given theta, right? Which is what we're trying to calculate. And this is the theta parameter, right? So of course, theta will be varying only between 0 and 1. Right? Why is theta varying only between 0 and 1? Because it is denoting the probability of a heads, right? Which has to be between a 0 and a 1. So we said that this is the graph which is showing the probability of the data set given the parameter theta. Why do you think it's peaking at around 0.8? So by the way, for this data set, we had 8 heads and 2 tails. We had 8 heads and 2 tails. If we plot the probability of D given theta, which is the probability of D given theta is probability of D1 given theta times P of D2 given theta and so on and so forth till P of D10 given theta. You multiply all of those numbers. So as a function of theta, we get a graph like this, right? So what can we see from this graph? That the probability of D given theta is maximized at what theta value? At theta is equal to 0.8. In this specific case, this function is maximized at theta equal to 0.8, right? So we call this particular point as the maximum likelihood estimate. You had this term likelihood, P of D given theta, which is a function of theta, right? Where is that function being maximized? At theta hat equal to 0.8, right? Does everyone agree with this? Right?
Yes,
So we first calculate the likelihood, in which we use the fact that the data is IID, right? Independent and identically distributed. Therefore, you can factorize the calculation of the likelihood like this, right? Once you've figured out the likelihood function, it's a function of the parameter theta, right? And then we are trying to see if we can maximize that function as a parameter, this function, which is a parameterized by theta, right? Now, once we get this theta, which is the optimum theta or the MLE theta, right? Now, this is one way you are able to tell which theta explains the data the best, right? This was the same thing you were doing when you were saying that Steve is most probably a librarian. You looked at the data, right? And then you figured out that maybe the most likely explanation or my best estimate for explaining this person's profession is that that person is a librarian. We're doing the exact same thing here, but in the context of a different problem for the coin toss, right? So what we've seen is that we said that we had data set of 10 examples, 8 heads, 2 tails, and the most likely explanation or the most likely value of probability of heads is 8/10. The way we have defined this is that we have calculated this likelihood function, right, which is a function of theta parameter, and we have seen that where does it maxima of this function occur, right? So this technique is called maximum likelihood estimation. Figure out the likelihood, maximize the likelihood, and figure out the theta at which the maximum occurs, right? Now previously also we have seen this. So we can in fact analytically also find out the value of theta for which this function will be maximized, right? So we've said that, and we can write it in this way also. H is denoting the number of heads, n minus h is just the number of tails, right? So probability of the data or the likelihood as a function of theta is theta to the power h times 1 minus theta to the power n minus h, or you can just write it to the power t, right? Now I have done something fancy here. I have taken logarithmic on both the sides. Why do you think we are doing that? So I had a function of P of D given theta, I could have directly optimized that. Optimizing a function means you calculate the derivative with respect to the only parameters, theta, set them to 0, and you will find out the optimum solution. But I'm not doing that. Instead, I have taken the logarithmic of the likelihood function, right? And I'm then trying to optimize that. Why do you think we're doing that? Why do you think it's a good idea? To simplify the calculations.
Sir, is it because if you don't log and then differentiate, you will keep getting theta power again and again, right? For example, so maybe difficult to solve actually.
Yes. So let's come back to the objective. We've for now defined this function, which is a likelihood function, right? Probability of d given theta. We have to maximize this function. So function of parameter theta. Maximizing a function means that we take the derivative of that function with respect to that parameter, set it to 0, right? We could have directly taken the derivative with respect to theta, set it to 0, and got this exact same answer, but the calculation is a little more involved, right? So that's one reason why we're converting this function log likelihood to a log likelihood function, and we're instead optimizing that, right? But why can we do this? So one is it's more mathematically convenient. But why can we, instead of optimizing a given function, optimize the logarithmic of that? Why do you think that makes sense?
So logarithmic is strictly increasing.
Yes. So the optimization of a function f and the logarithmic of that will return the same optimum value, because logarithm is always increasing. Like it's a monotonically increasing function. Therefore, optimizing either will result in the same answer. And yet another way to answer this is, so by the way, we can see the mathematical complexity being reduced. So previously you had multiplication of things. So finding the derivatives of multiplication of two things is hard, right? You have to apply the product rule and things like that. But finding derivatives of sums of two things is easier, right? And the other reason is that the powers, the exponents, they come down as a multiplicative constant that we're dealing here. So mathematically, it's much more convenient to use logarithmic of the likelihood and maximize that. Secondly, we can do this. This is the correct operation to do, because the logarithmic is a monotonically increasing function, right? So maximizing the original function and maximizing the logarithmic of it will result in the same answer. The third reason why this is mathematically very convenient is that, so theta is a number between 0 and 1. 1 minus theta is a number between 0 and 1. So if you multiply a lot of small numbers, which are between 0 and 1, what do you expect to get? Numerical underflow. Right? Numerical underflow means that your machine doesn't have enough precision in order to, so that it cannot preserve the really small numbers, the multiplication of really small numbers. Right? But if you convert them into log space, then you don't have that problem. Right? You're dealing with, yes. Yes. No. So that was, so previously it was the number of tails, n of t. So I think what you're getting confused is, this is probability of d1 equal to x. So the question is actually a valid one. So one, you're looking at the PMF of the Bernoulli distribution, right? This is the PMF of the Bernoulli distribution, which is theta to the power x, where x can be either 0 or 1. And the other thing is, once you've considered n independent identically distributed samples, then the likelihood function, which is p of d1, d2, so on and so forth, right? That comes out to be theta to the power nh times 1 minus theta to the power nt. So if this is confusing, then you can simply think of probability of d1 equal to x given theta is equal to theta if x equal to 1, or it's 1 minus theta if x equal to 0. That's a simpler way to write if this is confusing. Yes. So D here means the data set. D1, D2 is the number of, so D1 means it's either a head or a tail. So each of DI means it's a data observation. It's either a head or a tail. Theta is our parameter. So we're trying to figure out what is the probability of heads. Probability of, right, theta is the probability of heads. Probability of theta is the distribution you give to what you think about the probability of head. So it's a meta. Yes. So yeah. So if you just hold on for 2 minutes, we'll come to this question. So if we break the flow, it may get a little confusing. Let's first figure out. So is there any confusion in how to figure out the likelihood? Right. You can figure out the likelihood in this way. We can figure out the log likelihood. Right. And in this case, I'm just showing that if you calculate the d over d theta of the log likelihood, so it comes out to be h over theta minus n minus h divided by 1 minus theta, and you set it to 0, right? And that gives you theta hat or theta optimal equal to h over n. Now, this is the estimate you've been thinking all along, right? So you didn't actually need this exercise, but how do you get this? By maximizing the likelihood. You've got an estimate by maximizing the likelihood. In this case, you've actually done by maximizing the log likelihood, but there the solutions will be equivalent because why is maximizing the likelihood the same as maximizing the log likelihood?
Log is
because log is a monotonically increasing function, so maximizing either of them should be giving you the same answer. So next quick question: do you think this is the maxima or the minima? So from the plot, it was fairly obvious that it's a maxima, right? It's a maximum. Why do you? But if you had to prove this mathematically that this is a maximum, what do you do? Second derivative should be negative. And in this case, we see the second derivative comes out to be the negative number indeed, right? Now, Ashish discussed about using cost functions, j of theta or j of w, right? What has that got to do with what we've seen just a few minutes back? So we have seen that we can obtain the parameters theta by maximizing the likelihood, right? We're trying to say that figure out those specific theta which best explain the data. Right? Let me repeat. You're trying to estimate those theta which best explain the data or which maximize the likelihood. What has that got to do with the cost function which Ashish had presented in the morning? Yes. Yes. So what is the loss function? What is in general a loss function? Okay, so one at a time. Yes, you can go. Error between actual and predicted, but that error you define whether it's cross entropy error or whether it's squared error. Yes, other answers? Yes. What has that got to do with the likelihood function? Okay. Okay, good. Other answers? What is the relationship between log likelihood or likelihood and the cost function that we've been seeing? So does it make sense if we forget about what we did in the morning for just a couple of minutes? Does it make sense to think about maximizing this likelihood function as, so can we think of this likelihood function as a function which we want to optimize, as the function whose value if you maximize, you'll get the right set of parameters? Does this seem feasible? Does this seem correct? So just using that definition, the likelihood function we can think of as the cost function. In fact, it's the other way around. So other way around as in, so in Ashish's talk, he was telling about the loss function being something you're trying to minimize, right? And here we have looked at a function which is the likelihood function which we're trying to maximize. Right? So can we then think of negative log likelihood as a cost function? Yes. Can we think of negative log likelihood as a cost function? If we think of it that way, we are done. So that's the most important thing I want you to derive from this particular lecture. Deriving the likelihood, and then you can derive the log likelihood just for mathematical convenience. Negative log likelihood is a function which, if you minimize, will give you an optimum set of parameters. which best explain the given data set, given the current model parameters. Questions on this? It's a slightly harder topic to get started, but I'd love to have any questions. Don't worry if you don't get full of it. Okay. Right. So when we're thinking about the loss function, right? So what do you think about the loss? When we just literally hear the word loss, what do you think? How much loss will you incur if you made an incorrect prediction, right? So should you be maximizing the loss or you should be minimizing the loss? You should be minimizing the loss. So any one of you who's seen, who's ever invested into equities and stuff, like, do you want to maximize the red, or do you want to maximize the green? Want to maximize the green, right? So the loss is what you have in the red, right? So you want to minimize the loss. Now you want to maximize the probability of observing the data given the parameters theta, right? And that means you want to maximize the likelihood, which means you want to maximize the log likelihood, given log is a monotonically increasing function, which means you want to minimize the negative log likelihood, right? So therefore, if you can use a negative log likelihood as a cost function, right? The cost function was a function of what parameters? For logistic regression, it was a function of W and B or theta, right? What is the negative log likelihood a function of? Theta, WB, same thing, right? So therefore, these two terms are equivalent, right? Because you could either maximize the log likelihood or you could minimize the negative log likelihood. In machine learning and most of the routines you see, we are looking at minimizing functions. It's just a standard convention, but it's the same thing. Yes, questions? So we can then, yes. Loss is, so we generally say that the loss is the negative log likelihood. That's it. Yes, you can just say that. Now, what advantage does this framework give you? So for example, for the logistic regression, like one way to think about is that cross entropy loss makes a lot of sense, right? But does the squared error loss also make sense for logistic regression, for classification? Why not? So in fact, if you code it up, you should try this as an exercise. You may end up getting reasonably good results, right? But why do you think that's not being used? Sorry? Yeah. So machine learning people and mathematicians tend to think in terms of certain properties of functions. So what functions are good to minimize? What kinds of functions are good to minimize? Convex functions. So the cross entropy loss is a convex function for the logistic regression problem, whereas the squared error one is not. And we'll see that when we get to that specific lecture. But I wanted to show here that this particular plot that we've obtained, this is showing us the theta MLE or theta hat MLE, right? And this is the analytical estimate was as simple as H over N, right? The number of heads divided by the number of total tosses. And we've also seen that it's indeed a maximum, right? But we could have also used optimization. Yesterday in the tutorial today morning, you've seen that we could have used gradient descent, right? Now we have a function, which is the cost function, which is negative log likelihood. So if you see, it's a function of the theta parameter. So data is fixed here. So we can write the likelihood as the Bernoulli likelihood. So Bernoulli distribution, and you're giving the theta as the parameter here. So again, I don't want to be getting into all the specifics of the code, but all you need to write is you need to know the appropriate distribution, in this case Bernoulli, because it's a coin toss problem. It will be either heads or tails. What is the probability of heads? It's based on theta, right? And the log prob is likelihood.log prob of the data. So how likely, so given a parameter theta, Bernoulli distribution, how likely are you to observe this data? That is given by the log prob method, right? And that's what this log, this negative log likelihood function is showing you, right? And then you can use gradient descent as you've done earlier, which you can see that it will get optimized. And since it's a convex function, you'll easily get convergence. And it comes out to be roughly point. Like there are some optimization related things. You could have otherwise obtained an exact value of 0.8. Yes. Okay. Okay, excellent. So the question is, what does Bayesian update mean? So let's assume that we had observed absolutely no data, right? We have not done any experiments. We had a probability of theta, which is something like this. So this is also answering your question. So we initially believed that the coin could be, the probability of heads could be 0.01, it could be 0.1, it could be 0.2. All of these values are equally likely. You know nothing about this coin, right? What kind of a distribution is the blue line? Uniform distribution, right? So again, you might have thought in your earlier courses that why are we studying this? We are computer scientists. Uniform distribution, these distribution doesn't make sense, right? Let's start to make a little bit more sense. Uniform distribution, you don't know. So in this case, all you're saying is that the probability of heads could take any value between 0 and 1. Each of these values is equally likely. You don't know anything about the problem. You don't know anything about the coin, right? Is this the same as the coin is an unbiased coin? Is this the same thing or no? Why not? What does an unbiased coin mean? Yes. So probability of heads is 0.5. Is that a distribution? What about the delta function, the delta distribution? Again, something we studied in what course? Signals and systems, and we didn't have to study about that again. Yes. So if we had all the mass at theta equal to 0.5, right? Would that have been the delta distribution? Yes. So that would have been, if you said that my prior knowledge, you are fully confident in the prior knowledge that the coin is unbiased. Right? At this point of time, we know nothing. So we're saying that it's a uniform distribution. As and when you start observing some data, so you've observed data set point D1, right? You've then modified your beliefs a little bit, right? Your beliefs now become this orange curve. As you observe more data, you then change your beliefs even more. And your beliefs are now P of theta given D1 and D2, right? So which means that now they're more swayed by the data, right? And as and when you collect a large quantity of data, your prior beliefs hold lesser importance, right? Does everyone agree on this? As and when you have a lot of experience, you've seen a lot of data, your prior belief has lesser importance, right? Your parameter estimates are mostly going to be governed by the data that you've observed. But in small data regimes, that's where Bayesian learning becomes extremely well suited. And in online learning also, when you're getting more data, right? You want to have estimates which are also factoring in the prior distribution that you have. In this case, so that depends. In this case, you could assume D1 to be a set of data points. You could assume it to be a single point, but as per the convention, this is a data set 1. You could have 10 coin tosses. Right? Yes, other questions on this? Has it already been a lot? Little heavy? Yes. So binomial distribution. Okay. So what is the relationship between binomial and Bernoulli? Yes. So if my question, so let's look at these two questions. If my questions was, this is my question, what is the probability of getting this exact sequence, right? That is governed by the Bernoulli distribution. But if my question was, what is the probability of just getting 4 heads? What is that governed by? The order. If the order doesn't matter, then you use the binomial distribution. That's the relationship between binomial and Bernoulli distribution. So his question was, so in fact, we've not come to the machine learning aspect of things yet. We don't have an X here. We just directly looking at the observations here. When we come to that, then we'll be able to answer a question as in. So his question primarily is that for binary classification, Bernoulli distribution makes sense. But if we have to use, let's say, multi-class classification, what do we use? Any answers on that? Sorry. So you need to then extend the Bernoulli distribution to higher dimensions. So here you only have probability of heads and probability of tails. You have 2 numbers which sum up to 1. If you had 3 classes, you would have 3 numbers which sum up to 1. And that's called the multinomial or the categorical distribution. But we'll come to that in a few minutes. So this is a toy problem where we just specifically showing that if this is a given data set, then what distribution you should be using. As such, the parameters won't change, right? Because you're just dealing with the external constants. Yes. The sequence of data. So is that a question? Is that an answer? Okay. And this, so right. So it's actually a very good question. Does the sequence matter in this online learning like fashion? In certain settings it will, in certain settings it will not. So when we study the beta distribution, which we'll study in a few minutes, right? There we'll be looking at only the total number of heads. And so let's say if D1 had D1 heads and D2 data set at D2 heads, right? Then eventually this final distribution will just be governed by D1 heads plus D2 heads. It won't be governed by whether you had more heads first or lesser heads. Eventually, when you talk about the green distribution, right? So that's going to be governed by the total number of heads you've seen thus far, irrespective of the order. But we'll come to this, that how does this updating happen? Yes, was there another question? Okay. Okay, so let's now think about this scenario where we had the MLE estimate as H over N, or the number of heads. Right, we have this MLE estimate. Number of heads divided by number of heads plus number of tails. Right. Now assume a data set where you had 10 heads and 10 flips. Is the probability of heads equal to 1? Can we conclude that? Why not? Why not? Okay. Other answers? So in 10 flips, if we see 10 heads, can we conclude? So we've just seen the formula, right? We have done gradient descent, or we have done analytical solution. We've figured out that the probability of heads is number of heads divided by the number of total flips. 10 tosses, 10 heads, is the probability of heads 1? Sorry? Yes, it is 1. So can we use that? Should we be using that number or not? Okay, excellent. So that's a, sorry, go ahead. Okay. So let's say, let me ask you this question in a slightly different way. 10 tosses, 10 heads. Should I be concluding probability of heads equal to 1? But let me ask you a different question. 10,000 tosses, 10,000 heads. Can I now conclude probability of heads equal to 1?
Yeah.
Or is it the same thing or not? That's the question. Right. So let's talk about the difference between these two things. 10 tosses. So let's say that you are, I don't know, you're dealing with, you're looking at two different teams, right? Team A is some very good team in football, and team B is very, very bad. You've seen only two matches. In both those matches, the better team won, right? Let's say, let's not take names, but let's say a top ranked team versus a low ranked team, and the top ranked team beats the low ranked team 2 times, right? So can we say that the top ranked team will always beat? We may not have that much of our confidence, but we've seen 10,000 games between those two, and the better team always won. Can you now conclude? Yes. Yes. Yeah, so actually you should be thinking in terms of limit infinity, but the question is only about relative confidence that you may have in it being probability of hits equal to 1. Yes. Yeah. So all of those things will matter, but my question is actually much more simpler. So will you have much more confidence in saying that this coin is indeed biased? It will be always a heads. If you had seen, let's say, 2 tosses versus you'd seen 1 lakh tosses. So it will be very unlikely that if the coin was unbiased and still out of 1 lakh tosses, each time it landed as a head, right? It's very unlikely that such a thing will happen, right? So this was the point which we made a few minutes back also. When you have a very large set of observations, your prior beliefs don't have a lot of significance. Then your data starts dominating your beliefs, right? So can we then conclude that theta MLE equal to 1? Is that a correct answer or not? Especially if the data set is small. Can we say if 10 tosses, 10 heads, theta MLE is the probability of heads equal to 1? Theta MLE will be 1. Can we conclude that probability of heads equal to 1? Can we conclude? Why should we not conclude? Because the data set is really small, you don't have enough confidence in the data set. So then what should you do? If you don't believe your data set enough, then what should you do? Add a measure of uncertainty, which is, what is that measure of uncertainty? Sorry? Given a range of values. In this case, you can't, because you're dealing with, so by the way, MLE is known as a point estimate. Why is it a point estimate? You're giving a single point. You can't artificially add some ranges to it. You have to do something else. You have to, as you mentioned, that you need to know, need to add notion of uncertainty, but where do you get that uncertainty from? Your prior beliefs. So go back again to Steve the librarian, right? Or some other, you go back again to the Bayes rule, right? So what do you think is a prior belief when you start tossing coins? That the coin is generally unbiased, right? That's what we start with, right? We want to give the coin a fair chance to, we want to think that the coin is fair. And then if you keep on tossing, keep on getting heads, maybe it isn't biased. So then your prior beliefs are wrong. You need to update your beliefs. You need to set them to what you currently have. But that's the question. Given only 5 tosses, we cannot conclude that the probability of heads is 1 if it lands heads all the time. Should it be something less than 1? Should it be between 0.5 and 1? We will apply the Bayes rule only, right? So if we apply the Bayes rule, a Bayes rule looks something like this, right? So now what we want to do is we have the likelihood term, which if we maximize, we get the theta MLE, which is number of heads divided by the number of total tosses, probability of theta, right? So this is your prior beliefs about the probability of heads, right? And you want to incorporate that also in order to get your posterior beliefs or your updated beliefs about the probability of heads, given that you've observed the data, right? So you need to incorporate both things. One, your prior beliefs. Second, your data that you observed, right? So I think let me see if we can quickly cover a little bit more ground. So this is the problem with MLE, right? MLE does not handle prior knowledge, right? And the second, MLE can overfit. Now, have you heard of the overfitting term earlier? Where did we hear it? In the lecture in the morning. What did we do when we heard the term overfitting? How did we solve that problem? One at a time. We added some penalty, right? So in the Bayesian setting, we'll see that the penalty comes naturally. So when we incorporate that prior knowledge, that acts as a regularizer, right? And that's the whole point of discussing this specific framework. The prior probability leads you to having inherent regularization, right? And the fact that the maximizing the log likelihood or maximizing likelihood gives you the loss function, right? Maximizing. Okay, let's go back here. Bayes rule. Maximizing this term, the likelihood term, gives you the loss. So this is the loss function. P of d given theta is the loss, and P of theta given d can be thought of as the regularized loss. So once you've added the regularization term is, so what was the kind of regularization term that we generally added in Ashish's talk? Lambda 1 into what? Summation of weights. Did we ever do that? Summation of weights? No. Either the absolute value or the squares, sum of squares, right? And we'll see that both of them come from certain specific distributions. So if you use a normal distribution on the prior, you get L2 regularization. If you use the Laplace distribution, you get the L1 regularization. So that's the unifying framework. So post lunch, we can continue this discussion, and then we'll look at the posterior estimation, and then we'll come on to linear regression, and then hopefully we'll be able to derive the cost function for logistic regression, which is the cross entropy loss. So I think we should end now. Can we start a little early, because I think I'll be out of time, I think, because I've gone